Hello, I'm Jesse. I'm going to be talking about the skinned and swept surfaces. We diverge from the idea of swung surfaces and this idea of swinging curve around an axis. We set up a section of curves, a set of curves. Now we parameterize our XYZ axes in this U and V directions, where U is the XZ plane and V being the XY plane. And we create this set of curves in the U direction. We can mathematically define creating a surface based on this set of curves, based on B-splines with the equation here. And from here, interpolation occurs in the U and V directions. Now, I wanted to bring this up at the beginning. I feel like these four things here, parameterization, positioning, continuity, and weight, are very important concepts, not just in geometrical modeling, but also in a lot of math problems in science in general. So this idea of parameterization can refer to our U and V directions. Positioning refers to our set of curves being laid out. Continuity is our functions that we'll be using, continuous functions. Weight are parameters to scale, our knots. So we have this set of curves, and they all have different degrees, different common, different knot vectors. So we need to find a common knot vector in the U direction among this set of, we have 5 curves here. So this was called knot refinement. It was covered in a previous section. We do knot refinement, and we find a common vector and a common degree. And our common knot vector ends up being having 22 control points in the U direction. So it's quite a few points with any sort of larger surface. This number 22 could really increase exponentially and become quite unmanageable, I'm sure. So when we set up this 22-point vector, we essentially now have a grid of points in the U and V directions, and we can interpolate in the U and V directions and actually create a surface this way. This method can be very difficult to control exactly what the surface is going to look like. So to gain more control, we can construct a spine curve in the V direction, which we will interpolate across. So there is an equation here for the spine curve. Now our skinned surface is split into this spine curve and a set of cross-sectional curves. This now gives us a sort of skeleton or scaffolding for our surface in 2 directions, one in the U direction, one in the V direction. We have to consider what type of curves we're using in surface construction. The curves can be rational, non-rational, planar, non-planar. But depending on what kind of curves we're using, you're going to have to use a different method for surface construction. Non-rational curves, interpolations can be carried out in 3 dimensions, whereas the rational curves will need a 4-dimensional homogeneous space. We can calculate derivatives along the spine curve, which end up being perpendicular to the U curves, parallel to the V curves. These derivatives can help us in our surface construction process. This is an example here of using the derivatives, which I call vector V here. And you can show there's some you can see there's some calculations. So the derivatives provide constraints for calculating a surface, thereby giving gaining a little more control over what the surface is going to look like. So here we can see two surfaces, one on the left with derivatives, one on the right without derivatives. The actual bottom portion is a little tough to see the difference. On the top we can definitely see a difference in the control points, the way that they were being interpolated. We could change our spine parameters. This picture demonstrating how the distance that our section curves are being spaced out. Right here on the left, the distance is less. So there are issues with skin surfaces that can result in this switching back between 3 dimensions and 4 dimensions, and what kind of curves we are using to construct these surfaces. And we can utilize a smoothing function to scale our curve set in 4 dimensions. I didn't really get to the details about the smoothing function here, as this is I kind of thought this was a more advanced topic. Here are some examples of skin surfaces. The picture on the left, as we can see, is kind of becoming more controlled as we go down, from the top down. At the top, it's kind of wild. It kind of gains more control going down, smoothing it out. The picture on the right really is a good example of showing this set of curves that we're using in the spine. As you can see, the spine is right down the middle. So again, we want to come back to these 4 variables. We have parameterization, positioning, continuity, referring to the functions that we are using for curves. Weights are referring to scaling our curves. Positioning being where our curves and our spine curve are actually placed. Can make a big difference. All these things can make a big difference on the surface that is generated. These things can also make a big difference in other areas of science as well. These things kind of pop up, and these are kind of things to watch for in other problems also. So now we move on to swept surfaces, and we can give a general form of the equation for a swept surface, such as given here. So we maintain our u and v parameters and directions. We introduce this trajectory curve and also this scaling and rotation concept. Now we could set up the problem as given here and we can actually solve this analytically and construct a surface this way. This is shown in the picture. However, the previous method was limited in that the rotation would actually have to be the identity matrix. When this is not the identity matrix, we need to formulate the problem differently. It no longer is an analytical solution with an equation that we can solve. It's a algorithmic process, numerical method to solve this, construct this swept surface now. So we use a global coordinate system and introduce a local orthonormal coordinate system with OX, Y, Z vectors, which moves along a trajectory curve now. Local orthonormal coordinate system, our XYZ coordinate system, is orthogonal. Normal referring to these normalizations that are occurring in our X, Y, and Z coordinates. Now we define our surface, our swept surface now differently, this equation, where we introduce this trajectory curve, this transformation matrix, and this diagonal matrix. This is representing these rotations. So like I said, now we need numerical methods to solve this equation, and we construct algorithms that will They're already constructed algorithms that are shown in the book. So we can combine skinning when constructing a swept surface using this trajectory curve interpolation, and the trajectory being in the B direction. There are two algorithms given in the book. Algorithm 2 does not use trajectory interpolation, as shown on the top. The first algorithm uses trajectory interpolation and is shown on the bottom. I don't really go into the details of the algorithms here, besides the trajectories. And we can talk about twisting our trajectories. Again, these are the algorithms. Interpolation of the surface with trajectory and no trajectory when twisting. You see the trajectory definitely follows a path. When twisting and rotating surfaces with trajectories, they can exhibit this offsetting phenomenon where there are oscillations, self-intersections, interference from the points themselves that are generating the surface. So this is another issue of control in building surfaces. To deal with this, we turn to this B vector that I didn't really talk about, which is an orientation function for calculating coordinates, as we can see. Now we are calculating our Z coordinate based on this B vector. We can use a Frenet frame to calculate B, so our B vector, assuming our trajectory is twice differentiable. And we also end up with this end term when doing this. And a Frenet frame introduces another local coordinate system that moves along the trajectory curve. So kind of interpolating locally along our trajectory curve for this Frenet frame. All other issues that I've gone through, going through these surface techniques, we find one technique that works, but then we run into an issue with it. Frenet frame has issues at inflection points, interpolation, shrinking. Here in the picture, down to almost seemingly a single point there. Maybe it is, I can't quite tell from the picture. There are definitely ways to deal with this inflection point, but I'm going to kind of leave it here on these swept surfaces. Now again, in swept surfaces, we come back to these four concepts, these four variables. You can say parameterization, positioning, continuity, and weight, which themselves give you parameters. And we need to consider all of these things as we construct our surfaces.